So this is going to be our final portion of chapter 3 in our lecture, and we're going to be looking at the algorithms for multiplication and division, how they relate to mental math or mental computation, as well as estimation. So we're going to look at properties of exponents and how these properties can be used to develop what's happening with multiplication and division so that we see that they're interrelated. We're going to look at some models for multiplication and division. We're going to look at using them to solve problems. We're going to, again, take a look at number systems other than base 10 so that it gives some insight into what is happening in base 10. And we're also going to look at mental multiplication. So the first thing is a property of an exponent is that an exponent is going to be written as repeated multiplication of an item. So 2 to the third is 2 times 2 times 2. So when we teach exponents, we really want to interlock the idea of exponents and multiplication. They're very highly related. And for this reason, when we have whole numbers or natural numbers that are being multiplied and have the same base, then we're going to be able to add the exponents together. Now, I'm putting a larger view video of exponents into the announcements this week with some examples of these properties. I really advise you take a look at them because I'm not going to get really deep into these properties at the moment. For any whole number, a and natural number, m, if I take it and I raise an exponent to an exponent, I'm going to multiply them. If I multiply two bases that aren't alike, so I have a and b, they're not the same thing, I can write them as the product raised to the exponent itself. And when I divide, I subtract. So this is going to be some short examples, but I'm going to have some more in-depth examples in a separate lecture for those that really want to dig into this or maybe haven't seen exponents in a while. So in part A, what I need to do here is I need to have the same base. So I see that 2, 8, and 16, and I know they're all powers of 2. So 8 is 2 to the third. 16 is 2 to the fourth. So I'm replacing 8 with that 2 to the third. I'm replacing 16 with that 2 to the fourth. Now that I have a like base, because they're all 2's, I can take them and add their exponents, and it condenses it down into one answer. So then if I'm looking at part B, I'm going to do my order of operations first, and I'm going to work with what's in the parentheses. Well, 9 and 36 are not the same base, but I can rewrite 36 as a power of 2 or power of 3. So what I'm doing here is I'm taking this 9 to the fourth is the same as 3 squared. So because 3 squared is 9. And then I'm taking that fourth exponent and it's raising that exponent to an exponent just like I did in the previous example. Then I'm going to have 36 to the fifth power. So that's actually a typo there. 36 as a power of 2 is it raised to the fifth. So that should be 2 to the fifth raised to the fifth. And then if I'm looking at 3, I've got that. So I'm going to take them all. I've got like bases with my powers of 3, so I can add those together, but that's as far as I can really take it when I'm looking at the beginning. I see what they did here. Then I'm going to get 2 to the 10th, because if I have 3 to the 18th divided by 3 to the 18th, I would subtract and it would be 0. So that's why it's going to be 2 to the 10th. Here what we did was 2 squared is 4, so that's not a typo. And 9 is 3 squared. So what I did was it broke 36 up as a product of 4 and 9. And so that's what that happened there. But again, refer to the exponent lecture. I'm going to have more examples of this because you're going to see these questions in the lab. And I think if you haven't seen exponents in a while, it's worth digging into that lecture. So their multiplication algorithms are similar in concept to what's happening here. So if I have 10 plus 3 times 3, I can start pulling those numbers apart to make things a bit easier, okay? So when I'm looking at this, I have 13 times 3, which is 110, 3 ones, and then the 3 is just going to be 3 ones. So I can look at it kind of how I've pictured here with this hands-on portion of it. So 13 is 10 plus 3. Okay, and what I did was I said, okay, well, 13 is 10 plus 3. And if I multiply 10 plus 3 by 3, that would be 30. 10 times 3 is 30. 3 times 3 is 9. So I get 30 plus 9, okay, which is 39. So this is one way of, again, borrowing to give us back to those tens, those nice numbers that end in 0. Now, if I multiply by 10 to the n, this is going back to the base 10 information, I'm going to replace each piece with a base 10 piece that represents the higher power of 10. So if I look at this, each piece is going to be replaced with that base 10 piece. So I have 23 times 10. So here's 23 times 10 means I'm doing those bases. So yes, it's pretty simple to see 23 times 10 is, I think the trick that's usually taught is 23 and then put the 0 at the end. This is that trick. So this is when you're telling them when you multiply by 10, just do the 23 times 1, which is 23, and put a 0 behind it. That's the same idea here. If I want to do it using expanded addition, this is for advanced students. This is not for your average everyday student. Numbers like 4 times 367, I can break 367 down into expanded form, just like we did in week 1. And 367 is 300 plus 60 plus 7. So 300 is written as 3 times 10 squared, 60 is 6 times 10, and 7 is 7. So then I can distribute the 4 through, and then I can get my final answer. Why on earth do we want to teach our students this? Well, because starting as early as 5th grade, they're having to know the distributive property. So when we get to a point where we feel they're comfortable with multiplication, this is either an extension or this is for your students who are really excelling during multiplication, and it's something to show them so that A, they're getting used to the properties of exponents, and B, they're really getting that distributive property, which they're going to need in all their courses from 6th grade on up. So multiplication with 2-digit factors would be simply 2 digits, and that's going to be the standard procedure is kind of what this is showing is you're going to do, 4 times 3 is 12, 1 times, so you're just doing general multiplication. This is the everyday thing. This is what we teach. Vertical columns, there's a picture of this. We can do it with lattice. Lattice is going to work for your visual learners, possibly. Not so great for some of our not so visual learners. So we're going to put our 14 and our 23 right here. And we're going to start looking at what happens when I multiply 14 by 23. Well, I get 1 times 2, which is 2. 4 times 2, which is 8. So the lattice is going to have a 0 here because there's no tens value, okay? And then I'm going to look at 1 times 3 is 3. 4 times 3 is 12, so that's why there's a 2 and there's a 10 here in the box. So then I'm going to look at, okay, so this is what I have going on here. If I add 8, 9, 10, that's going to become 2 tens. If I add, so that's where that's coming from, okay? I'm looking at adding those tens in the lattice block. Again, this is going to be for your visual learners. It's definitely not a strategy we want to push students into doing if it doesn't make sense for them. So if you have a student who's struggling with multiplication, that's a possibility. Now, one of the things I mentioned in the discussion area is we are not using calculators to divide. We are kicking it old school with division. So we are using long division. I'm not going to go through long division because most of us should be familiar with this, but this is how we're more working, especially with the bases. And when we're first teaching division, we want to really teach it to the point where they understand what a remainder is. So some division algorithms, there's just different ways to write the long division. So you could have them say 6 goes into 7 one time, and it doesn't go into the other ones because there's no remainder here. And you could subtract 600, which gives you 126. So this is just kind of scaffolding the answer up, which I don't think makes sense for a lot of students. So this is kind of how I would suggest teaching it, but kind of keep this in your back pocket if you have a student who would rather write 120 and 1. So if they would rather divide that way and say, well, 6 goes into 7 one time, but then it's not going to have, that's the 100 is what it's got. And then it's going to go into 12 2 times with a 0. That is better for students who might struggle a little bit with place value. Using base 10 blocks to look at standard division algorithms, we can take those blocks and we can break them apart into 6 groups. So I've got 6 100s, every group gets a 100. Then I'm going to break up that 10 block, give everybody, and I'm just going to distribute it to everybody to get the answer. And this is what it would look like. So again, that's kind of a manipulative way of having students break it apart and actually look at solving it. Short division, that's something that I learned, and I didn't realize a lot of people don't learn this way. So in short division, the difference is you write the remainder um, on the side of what's happening. So 5 goes into 28 5 times 5 is 25, and there's a remainder of 3. So that's why that 3 is here in front of the 8. So then you go 5 goes into 38. So instead of showing the subtraction, you're just putting that remainder right there. So 5 goes into 38 7 times with a remainder of 3 because 5 times 7 is 35. So then 5 goes into 7 6 times. Now, when I learned this, I just do this last piece. I don't do all 3 before it. I think too, as a teaching strategy, I would only want to show them this one piece, but this helped me illustrate what I was doing a little bit better, so I used it to show you guys. For two-digit divisors, we're looking to estimate, multiply, subtract, and then compare or check our answers. This is the four-step method for division. As we all know, students struggle a little bit with division, so we're trying to equip them with ways to kind of guesstimate a little bit and to also understand their answer and the context of what's happening. So if I want to estimate the quotient's going to be somewhere between 10 and 100 because 100 would be 3,200. So that's why I'm saying it's somewhere between 10 and 100 if I'm looking at whole tens. If I want to find the number of tens in the quotient, I can go ahead and launch into 32 goes into 261. How many times? It goes in there 8 times. And then I'm able to kind of guesstimate that it would be 32 times 80. If I want to find the number of units here, I'm getting the exact answer. So I kind of estimated. Now I'm doing proper long division and I have a remainder of 26, and that's my exact answer. A lot of what we're going to do is really related to needing those remainders. Then I can check my work. And so we want to teach students to check their work. And when you're checking your work with a remainder, you have to add that remainder in after you multiply the quotient. This is going to look at multiplication and division in different bases. So if I have 21 base 5, remember that's 2 tens, so it'd be 2 fives, because 2 is in the tens place, but base 5 means they're really fives. And then I have 1, and I'm multiplying that by 3. So I have 2 fives, 1 1, 1 3. I'm going to look at that as 20 plus 1, and 3 is just 3. So if I work this out, I'm going to get 110 plus 3 because you have to remember 1 times 3 is 3, but 3 times 2 is 6. And so 6 is 110 or one group of 5 and 1 1, which is where the 11 comes from. That's why 3 times 2 is 11 because 6 would be one group of 5 and one group of 1 because we're in base 5. And then we're going to add them together to get 113. So again, if your numbers are less than the base, there's really not much to be done, but it's when your numbers exceed the base that you have to start looking at that. Division is going to work the same way, but we're going to have to put things again in groups of by 5 and by 1s. So here's another example. If I'm looking at base 2, so if I'm looking at base 2, 1 times 1 is 1, 1 times 0 is 0, 1 times 1 is 1. Nobody's greater than 2. We're okay so far. Same thing. Add them together, and I get 1, 1, 1, 1. I don't have to worry about groups of 2 because every value is less than 2. If I want to do front-end multiplication, this is a mental type of math here. I can take 78 times 4, and I can make that 70. So 78 becomes 70, and then 8, and then I'm multiplying both of those times 4. Where does that come from? It's coming from expanded form. So expanded form, it's hard to get students to see it's important, but it really is. 78 is 70 plus 8. I'm distributing that times 4 to that statement to get to the multiplication. I can also use compatible numbers. So I can break things down. This is more for your advanced students to give them a look at something. Or you can start thinking about money. So I could start thinking about this as 84 quarters. And this only really works though when you're looking at 25. Breaking up the dividend can help. So if you've got something like 8 goes into 56 a very clear number of times, you can sort of fragment it. But this is just the method, right? This is going to be division in the lab. It's not going to be that we have to do it this way, like we talked about in the discussion forums. So this is another look at compatible numbers where I'm taking that 105 and I'm breaking it into two things that are factors of 3. Here's a front-end estimation problem. So I have 474 times 9, which would be 400 times 9, 70 times 9. Look at that expanded value. And I'm getting 3,600 plus 630. That's an estimate. I'm not dealing with that last 4 because I estimated it. If I want to look at compatible numbers, I'm going to do the same thing. I'm going to kind of round to a place where it makes sense for my divisor of 6 to be plugged in.